So we did talk about networking. We focused on networking on the last few videos, but there's one more topic here, very important one that we need to take into consideration, and that is network traffic. Whatever travels through that network, that's the purpose for which that network exists from the very beginning, to transport data from one point to the next. But there's also a lot of security information in all that network traffic, because most attacks out there are going to reach your network, your systems, your hosts, by using some sort of network, even if it belongs to you, even if it doesn't belong to you, even over the public internet. So network traffic is really important from a security perspective for attackers and for security professionals as well. So if we want to analyze network traffic from a security perspective, we first need a way to capture it in order to analyze it. Because normally you only get to see traffic that is destined to your own host, your own workstation. How do we capture traffic that is not destined for us? How do we analyze the entire network traffic on a single network segment, for example? And before thinking about the actual method that we can use to capture that traffic, let's think for a second about what kind of traffic we want to capture and what exactly do we want to analyze. Now, a first obvious answer to this would be to just capture the entire traffic that goes through a network segment. So we can perform something called an inline traffic capture. And it's called inline because you're actually placing yourself or your own device in the middle of a network segment that you want to monitor. So you could have something as simple as this: one host A communicating with one host B, and of course they do have some network segment between them. So how do we inspect what's going on through this network cable? Well, one simplistic approach would be to install an additional host right here in the middle, connected with one interface toward host A, one interface toward host B, and whatever traffic happens to flow through this network cable is going to be intercepted and analyzed by an application that is running on this host. So this one here, that's me, that's Andrew. Now, what are the pros and cons of this approach? Well, first of all, it works, and that's pretty much it. It just works. Now, as far as the cons go, well, it's intrusive, it's difficult to implement, because you actually have to break a wire or insert new wires, new connections in your networks in order to actually be able to install yourself into that traffic flow. Secondly, it doesn't scale. I would even say it doesn't scale well. It doesn't scale at all, right? You're only able to inspect that specific cable and that's it. You're not going to be able to do this on a larger scale with multiple servers, multiple network segments, even, I don't know, multiple internet connections. So it's not exactly the best way to do traffic capturing. So let's see some better ways. Now, a better way would be to configure your networking devices, switches most likely, with a functionality, a feature, which is called span if you're using Cisco switches. You're going to find it under the name of port mirroring or traffic mirroring under other vendors' products. But it basically relies on the fact that the actual network device can be configured to take all the traffic from one or more ports and create a copy of that traffic onto a different port where your packet analysis software is located. Now, there are a lot of ways in which you can actually implement span, and there are entire configuration guides on Cisco, for example, that explain, depending on your architecture, how to implement something like this. For example, you can perform span locally on a switch from one port to another, or you can perform it remotely, that is capturing traffic on one switch and then sending it over the network towards a remote switch. But that's beyond the scope of this course. Long story short, span or port mirroring takes traffic from one or more ports and creates an exact copy of that traffic onto a destination port. The only downside to this approach is that you actually need networking hardware switches that support this feature. So I'm going to talk about managed switches. The third, the final option for capturing traffic is one that we've talked about in a previous video, and that is performing a man-in-the-middle using ARP spoofing, ARP flooding, and first of all, this is only going to work if your network is not properly secured, so a network that doesn't implement DHCP snooping or dynamic ARP inspection. And secondly, it's pretty obvious that this is not the desired way of performing traffic capture. You're basically attacking your own network, so as far as the daily operations, daily business of an analyst or a networking engineer, you're not going to be attacking your own network and tricking your servers into sending you their traffic when you actually have more elegant methods of doing this, such as span or port mirroring. So it's a valid option, but it's not going to be the preferred option in an enterprise environment. Well, unfortunately, sometimes it's just not feasible or possible to catch all traffic and inspect all traffic, in which case we would have to just be content with a summary, a description of who was talking to who for how long, how many bytes were transferred, what kind of application was in there, kind of like the call log on your phone, where you can see exactly which phone calls were made, which phone calls were rejected, how long did they last, stuff like that. So it's basically a way to describe the traffic without actually looking inside of the contents of that traffic. You're not going to see the actual phone conversation in your call log. And in networking, we call this type of information a flow. Now, a flow is nothing more than a sequence of packets, a series of packets that all have in common a number of parameters. Like, for example, all the packets that happen to travel between one specific source and one specific destination, or for a one specific application. Now, grab all these packets that have this information in common, and that is flow information. That is basically a conversation, which is made up, of course, of multiple packets. And this flow information, you're going to find it implemented in a multitude of ways and under a huge number of standards and naming conventions, among which the most common ones are going to be things like Netflow or flexible Netflow. This is the one introduced by Cisco, by the way. You're going to find SFlow or JFlow from Juniper, IPFix, and others. Now, fortunately, even though many of these standards are actually developed by their parent companies, lately they have become interoperable. So you are now able to actually grab this flow information from multiple vendors, collect them to the same database, to the same appliance, and get a coherent view over the entire network, regardless of how many vendors you have in that network. They're all going to export information in the same manner, under the same standard. Now, of course, since we're talking about summarizing this information, summarizing the network traffic, we need the networking devices to help us do this kind of summary. So Netflow, as a generic term for all these flow technologies, has to be implemented on the networking device itself. That is most likely on the switch, on the access switch that connects these servers to the network or connects the workstations, or the aggregation switch that aggregates all these access connections. Now, these switches can be configured to look at the traffic that is passing through them, and every, let's say, minute or 5 minutes or 15 minutes, report to a centralized location, to a centralized application, a set of prepackaged information that basically describes this is the type of traffic that has been flowing through me during the past 5, 10, or 15 minutes. These are the top talkers. These are the destinations that I've seen. These are the applications that I've seen. This is how much data was transferred between this source and this destination. So all that statistical information is wrapped up nicely and then sent from the network switch to a management interface that is able to compile this information, store it in a database, and then later is able to perform some intelligent queries or generate some reports in order for you to be able to locate, for example, how much Netflix has the technical department watched in the past month. And you can gather all this information onto a centralized management console that is supposed to receive this Netflow traffic, where you can then generate some smart reports, which are going to tell you what kind of applications have been detected in the network, who is consuming the most bandwidth, which destinations or which servers have been accessed the most, or even security-related information. That is, figuring out if there are data flows, there are data streams happening in your network that shouldn't be there, like virtual machines communicating when they shouldn't, clients accessing remote locations on the internet that are known to be malicious. All right, so let's see what exactly do we need to capture all the traffic, or just to capture this summary information. So in order to inspect the entire traffic or to perform full packet inspection, first of all, you need a copy of that traffic. So you either capture it directly inline, or you use a device like the one that we've talked about before, using span functionality on Cisco switches or port mirroring functionality for other vendors that are going to generate an additional copy of the traffic that you can then later on analyze. Now, a second solution to this is especially in situations where, let's say, the networking devices, the switches, don't support this span functionality, would be to use a dedicated device called a sniffer or a tap. That's a test access port. Now, a tap can be either a passive or an active device, but its main purpose is to generate copies of traffic that comes in one or more ports. So it's basically not a switch. It's just the span functionality from a switch implemented in a completely separate hardware device. So in our ugly drawing here, we would have something like this, with this device in the middle now being a tap, which has dedicated interfaces. All right, we have those two interfaces that intercept traffic from A to B, and we have one more interface right here at the bottom to a dedicated management and monitoring host. So this is where the traffic now gets analyzed. Now, whatever traffic happens to flow between, let's say, A and B, all that traffic, of course, is going to flow in the right direction, but a copy of that traffic is also going to be sent to this analysis device here at the bottom. And this is where we can generate our reports, and this is where we can store that traffic and then further analyze it. Now, this approach, of course, provides you with a great benefit that you get to see the entire traffic that goes through that network segment. That's the good news. Now, unfortunately, there's also some bad news. The bad news is that you get to see the entire traffic, which, if that traffic is directed to or from a port on a server, that is, let's say, a 10 gigabit port, a 40 gigabit port, a 100 gigabit port, an uplink port, that's going to be a whole lot of traffic in there. And you might not be able to analyze that traffic at the speed at which it comes into your analysis device. Not to mention that if you want to just store it and then later analyze it afterwards, maybe perform some forensic investigations, the amount of disk space that you're going to be consuming is going to be huge. So as best practice, try to use this kind of traffic mirroring, storing, and analysis only for critical network segments or critical devices in your network that you absolutely have a very good reason for capturing, storing, and further analyzing that type of traffic. Otherwise, it's going to consume a lot of resources, and resources mean money. Well, that's it for the hardware side. Now on the software side, that is the application that actually looks for that traffic and is able to generate some useful information by analyzing that traffic. Now we have a number of tools in here, among which the most two popular ones are TCP Dump and Wireshark, and you probably heard about these two before. Now, TCP Dump is a command line utility, so nothing spectacular here, but it's really, really powerful. Now, at the minimum, you can launch TCP Dump using the simple TCP Dump command here, followed by the -I switch, which specifies a certain interface to listen on. In my case, ETH0, press enter here, and in a couple of seconds, you should be able to see all the packets that are flowing over my networking card. In this case, this is a virtual machine, so there's not much traffic going on here. But for example, we can see some ARP traffic. That's a request on the first line and a reply on the second line. You can see the timestamps. You can also see which IP address and which ports are being used as the source and as the destination, what type of packet is, and the length. Now, we can, of course, cancel this. I'm going to see a summary of all the packets captured, and we can actually tune this type of packet capture some more. If you want to see a complete list of all the possible switches and commands, of course you can use the manual page for TCP dump, starting with man TCP dump. And among the interesting switches that you can look for is the -N. Let's look for it. You can see it here. Don't convert addresses, host addresses, port numbers. So I'm going to see the actual IP addresses and port numbers as they are. So we're not going to wait for any DNS resolution happening in there. Another interesting one is -e, that is print the layer 2 header on each line. Let's try this out actually. So TCP dump -I ETH0 and add a -e at the end. And now you can see that you can also watch the actual MAC addresses from the source and the destination MAC addresses of all the packets that are going through your network interface. Other useful options here would be -v. This one is going to print out more information about your IP packets. So for example, the time to live, total length, and IP packet options are going to be printed. You can also upgrade this command with a -v -vv here, even more verbose output. Additional fields are printed, and up to 3 Vs, all right? So this is going to provide you with a lot of output. Now let's try this. Actually, let's see how it works with at least one single V. Let me just open a web browser here. So that is going to generate some traffic. And indeed, yes, we do see a lot of traffic here. Let's actually cancel out of this scrolling output. Now you're going to see that each packet now includes a whole bunch of information. So not just the MAC addresses, the layer 2 information, but you also see the flags, the time to live, identification, offset, which protocol, transport protocol is embedded in that IP packet, and so on. So a lot of information here, basically a packet dump. Now, as you can see, in just a couple of seconds here, we managed to catch almost 1,000 packets. So that's going to be a whole lot of information that needs to be processed, which is why TCP Dump also provides you with the option of saving this capture, this packet capture, to a file, and that's going to be the -w option right here. Right, -w writes the raw packets to a file rather than printing them out on the screen. This is basically going to generate a PCAP file, and the extension PCAP you might recognize from Wireshark as well. It's actually the same type of file. So files generated with TCP Dump can be opened in Wireshark and vice versa. That's going to be the same type of packet capture file. Now, of course, these files can be then loaded back into TCP Dump for further analysis using the -r option. So -w for write, -r for read from a packet capture file. Now, Wireshark, on the other hand, is a bit more user interface friendly, so we can start our capture, for example, on our Ethernet interface. And we're immediately going to see all the packets flowing through our network interface. You can see that the protocol is being highlighted here. Now let's just stop this capture for a second and select one of these packets here. So with this TCP packet selected, we can collapse these sections here at the bottom and can see that the first one actually refers to the layer 2 information. That's the framing information. You can see the frame length here, the number, and then right next to it, the Ethernet information. That's the MAC destination and the type of protocol that is embedded in this frame. In this case, it's IPv4, so we can further collapse IPv4 here and see all the fields that you should be familiar with from your networking trainings in a normal IPv4 packet. Of course, further deeper on the in the packet, we should be able to see the transport protocol, which in our case is going to be TCP, and we have a source port, we have a destination port, forward 3, this is going to be HTTPS, and then all the necessary session information like acknowledgements, window size, sequence, flags, acknowledgements, SYN flags, and so on, relevant for any TCP packet. Now, at the very bottom of the screen, you're going to see the exact same type of information, but this time structured in a raw display. So on the left hand side, there's going to be the hexadecimal display of the actual contents of the packet, starting with the layer 2 information and continuing with the payload itself. On the right hand side, you're going to see an attempt to display this using printable ASCII characters. Now, of course, since this is an HTTPS packet, this information is not in clear text. So what you're going to see here is either nothing printable like a dot or just gibberish, right? Because that's encrypted binary data. There's no way we can actually display this as a clear text right now. Now, I would strongly suggest that you take some time and play a bit with TCP Dump and Wireshark, not only because they're important for the exam, but they're also Swiss Army knives, the basic tools that any kind of networking engineer, security engineer, any person who is tasked with observing what's going on inside of a network should be familiar with. Now, there's an important difference between packet analysis and protocol analysis, and the exam is going to insist that you know this difference as well. So starting with packet analysis. Packet analysis is a type of deep packet inspection. That is, deep analysis of each data packet frame by frame. Looking at the headers, looking at the contents, looking at the entire data that comes in through the network interface card. From a security standpoint, depending on just how smart your analysis tool really is, it can help you identify by looking at the actual packets, things like command and control traffic, malicious URLs, data exfiltration attempts, if you find, confidential files in those data streams, right? Basically, any trace of an attack that uses the network is up to some point detectable just by looking at the network traffic. You're not always going to be able to look at the network traffic in real time. That is, you might realize that you've been breached, and you might have to look for proof of that breach into some traffic that happened a few hours ago or a few days ago. So this is why working with offline packet captures like those PCAP files that can be generated by TCP Dump or Wireshark, and having those files ready whenever you need to investigate something is really useful. But just having that type of traffic is not enough. You still need a tool to be able to reconstruct actual data streams and conversations and files from that content. These type of tools are called file carving tools. You give them a packet capture and they try to extract any kind of files that have been transferred using any kind of protocols within that packet capture. Some examples of such tools. Network Miner. You can see among the first features here, it has support for live sniffing of packets and also parsing of PCAP files. So we can either look at the traffic in real time or we can look at the traffic that has been saved on the disk previously. If you scroll down here, you're going to see that it's able to extract files from all these supported protocols. You can probably expect to find things like FTP or HTTP or server message blocks, SMB, the Windows file share, SMTP, and so on. You can also extract certificates or decapsulate tunneling protocols. Isn't that smart, right? And the most important thing on this page is the fact that it has a free edition as well. Another open source tool is Suricata, which you can see it's actually a network IDS, IPS, and network security monitoring engine. It's open source. It actually has a lot of functionality. You can have a look over the official documentation pages here, but under the section of rules, for example, you can quickly see a list of supported protocols. So these are all the protocols that Suricata can inspect and potentially extract useful information from any kind of traffic that might contain something like a sensitive file, a certificate, or basically anything that can be matched by a rule or a regular expression. Another famous tool for packet analysis and also network monitoring is Zeek. Now you can see it says here formerly Bro. That's the old name of this software. Make sure you remember this one as well in case the exam asks you about it. So an example here, simple one from the official documentation, you can see that Zeek can be launched to work with PCAP files generated by Wireshark or TCP Dump, and it can then generate and extract in a couple of log files all the information that it finds within that traffic capture. For example, the connections, DNS information, whatever files or HTTP traffic was detected within that PCAP. You can see some examples here as well. These are the connections, and this is the DNS log. Okay, you can get to play with this one as well. Generate the traffic capture on your own using Wireshark, then try analyzing it with Zeek using the official documentation, or at least the simple examples that you can find here ready-made. Well, you might be thinking now, well, that's great. I can just look at the entire traffic in my network, or at least the traffic that goes to my critical servers, and I can find all the malware in there. I'm safe forever. Well, yes and no. There are some problems with this approach. First of all, traffic capture is going to generate huge data sets. Difficult to store, difficult to analyze. Another issue is the fact that most of the traffic nowadays, especially web traffic, is encrypted traffic. If you cannot catch that traffic somewhere where it is in an unencrypted form, or you don't have the right certificate to decrypt it, you're going to have a hard time figuring out what exactly is happening within that encrypted traffic. Another potential problem is the fact that these file extraction tools try to identify whatever content within that packet capture is a file by searching for specific types of file headers. That is, the first 64 bytes in any file is going to tell the operating system what kind of file is it. Is it a JPEG file? Is it a Windows executable file? Is it a Mac OS executable? And so on. Now, the problem is that this information can be forged, can be faked. The attacker can obfuscate the malware file and make it look like a different type of file, knowing that on the other hand, there is some piece of software that belongs to the attacker that knows how to interpret that file correctly. But this kind of evasion might actually bypass your file monitoring tools or DLP solutions. Also, you might be looking at traffic that's happening on non-standard protocols or non-standard ports, and you're not going to know how to assemble that kind of information to make some sense of it. You're going to have a hard time identifying what type of protocol is actually traveling on that specific port. So yeah, all the information regarding attacks and malware is there, but you also need a bit of luck and a bit of intelligence to figure out what is the important stuff in all that traffic. Now, on the other hand, protocol analysis deals with just looking at the protocol part of the traffic. That is layer 2, layer 3, layer 4, of course, transport, and perhaps just some basic information about the application layer. Well, what can you analyze just by looking at the protocol and not the payload itself? Well, fortunately, there are a couple of things that you can determine. For example, you can find protocol anomalies. So packets that are expected to follow a specific protocol, like the HTTP protocol, but they don't exactly set the right flags, or they don't contain the right structure for an HTTP conversation. That might be an indicator of non-standard traffic that it's attempting to exploit a vulnerability or a bug in the implementation of the web server on the other end. You can also detect unknown protocols, because if you find some type of traffic in your network and you're not able to determine what type of protocol that traffic is, that's never good news. Nowadays, you can determine even the difference between, I don't know, a user playing Fortnite and a user playing World of Warcraft just by looking at the network traffic generated by those two applications. You can also perform statistical analysis. That is, looking for a certain sequence of packets or a frequency of packets that might indicate an attack pattern. And finally, we can even get some insight onto the actual application within those packets, even when the contents are encrypted. For example, multiple short exchanges might indicate some type of interactive session. A large one-way transfer might indicate data exfiltration, even if the transfer is encrypted. Cisco, and by the way, they're not the only ones doing this, they have a solution called encrypted traffic analysis, and they claim to be able to, just by looking at the network traffic, the encrypted traffic itself, they're able to find cybersecurity threats within that traffic without decrypting it. Now, of course, since it is not able to look at the actual traffic, it's going to rely on some advanced entity modeling and machine learning, right? Trying constantly to identify who is on the network, what are they doing, so that they can detect anomalous behavior in real time and to identify the corresponding threats. And don't forget that you can also use Wireshark from some very basic traffic statistic or traffic or protocol analysis. Like this one right here. This is the output from the flow graph functionality in the statistics menu. And you can even get some insight about protocol anomalies and errors and things that might be worth investigating by accessing expert information from the Analyze menu in Wireshark. And as you remember, the second method that we mentioned about analyzing network traffic is analyzing this flow information. And this is relevant because most of the time you'll probably not have the necessary resources to perform full packet inspection, full packet capture in order to determine suspicious activity. Now, especially in large environments where the amount of traffic is absolutely huge. So we can use another method just by capturing this summary information. Now, the good thing about traffic flows is that they don't require a lot of storage space. They don't require a lot of CPU to analyze, to process. And this information can actually be generated by a number of networking devices like switches, routers, even firewalls or IPSs, or even wireless LAN controllers for wireless traffic. And these devices send them from time to time to a centralized database or a management application for storage and processing. Now, if you have the right budget for this, such an application can also be a SIEM, a Security Information and Event Management, because that's a type of software solution, security solution, that is perfectly suited for analyzing this type of dynamic information that is coming from the network. So Netflow traffic sent to a SIEM can allow that SIEM to determine whether something malicious is happening in your network. Let me actually show you what kind of information are we sending within these flow technologies. So at the minimum, you're going to probably think that you should be able to send things like what kind of protocol we're using. Let me see here, the TCP control bits, IP class of service, source and destination, like the transport port for the source IPv4 address or IPv6 if it's necessary, ingress interface, egress interface, destination IP addresses, destination ports. But also, if you scroll down here, down this list, you're going to see that these technologies are actually extremely flexible. So we can actually go as far as sending specific BGP metric parameters along with our traffic. When did the flow start? When did the flow end? What was the minimum or the maximum packet size that we were able to observe during that flow? What kind of sampling intervals or sampling algorithms are using? And by the way, sampling is a very important topic because most of these flow technologies that we've mentioned before, they don't look at every single packet. They're going to look at 1 in every 10, maybe 100 packets, and that's all the information that they're going to process. All right. Why do we do this? Well, because we have to actually rely on the hardware of that networking device to generate this information for us. And some of them, especially switches, they are great at, just pushing traffic from one port to the next and then forwarding traffic. They're not so good at looking at that packet and making some smart decisions, maybe summarizing some information and storing it into a temporary memory. They might not have the necessary CPU power to do this for each and every packet. So if we ask this kind of summary information from them, not only we're going to receive just the general information about the flow, but we're also going to receive a general information of about 10% of the actual traffic that goes to that switch. Now, in most situations, this amount is going to be enough, but from a security standpoint, if we want to be able to pinpoint exactly what kind of attack is happening, who is targeting with using what kind of protocol, that's not going to be enough. Now, fortunately, recent devices have become more and more powerful, so unsampled Netflow is starting to become a standard in itself. And by the way, Cisco was the first one to introduce this technology, and they call it Netflow. Now, since the first version of Netflow, there have been a huge number of additional versions, each and every one of them expanding the ones before it. So right now, the versions that we're currently using are not only extremely flexible, but they're also standardized. So they're used by all the vendors out there, not just Cisco. So among the pros here are the fact that we're only capturing the metadata, like the source and destination IP addresses or the ports, the layer 4 protocol, stuff like that. Now, newer versions can also capture some custom fields or even routing protocol information, like the BGP fields that we saw earlier. Another benefit is the fact that you don't actually need any specific dedicated hardware to do this. You don't need to install anything new inside of your network. You just have to reconfigure the devices that you already have. Of course, you will need an additional component, and that is the centralized storage component, where all this information is being sent, stored, and analyzed. But that's another discussion. As I said, we now have a unified view among vendors, so most of the flow protocols supported nowadays are going to be common between multiple vendors out there. So when you aggregate all this information, it's going to look the same. Doesn't matter if it comes from an HP switch or from a Cisco router. And they're great for reporting and visualization, creating reports, traffic reports, who were the top talkers, who were the most used protocols, who was the most accessed destination in our company or in our department. Now, as for the cons, of course, we don't have visibility inside the actual payload, the actual packets. So malware is going to go undetected, at least the body of the malware itself. That's why with Netflow, we're looking at traffic patterns, because we're not able to look at the actual package contents. As I said before, you will need an additional component. That's the centralized storage and management component, which can be a virtual machine, an application running on a server. Just make sure that it is able to process the amount of flow information that you're about to send to it. Flow information, unfortunately, is not something that can be manually processed by a networking engineer or security engineer. And as we previously mentioned, most of the technologies up until quite recently, they were based on sampled flows. So they were just sampling one packet out of 10, for example, and that was the information that they used to figure out what kind of flow is happening in there. All right, so what kind of tools can you use to process this flow information? There are some enterprise solutions out there, because this is not something that you would probably want to have in your home or your home office, but this is something you will install in an enterprise environment in a small to medium to large company. Well, one example would be the Network Traffic Analyzer from the SolarWinds portfolio. Another one would be from Manage Engine, Netflow Analyzer, pretty similar to SolarWinds. Cisco also has a dedicated solution for security intelligence, which is based on collecting flow information. This was formerly called StealthWatch, and you're still going to find it as StealthWatch because people still call it that. But right now, it has been renamed to Cisco Secure Network Analytics. Extremely generic name. Actually, I would much rather prefer to call it StealthWatch. And on the more free open source side, you can find things like Silk or Argus. I'm going to provide you with links in the description for all of these. Make sure you check them out and just try to familiarize yourself with their capabilities. You don't need to be able to install these or configure these for the exam, but you do need to know what they're good for. And finally, not exactly flow analysis, but it's worth mentioning here MRTG. That's Multi-Router Traffic Grapher. Bad name in my opinion. It polls network devices It's based on agents which report over the SNMP protocol, the state of those hosts, those devices in your network. They must be configured to send SNMP information to MRTG, of course, which is just a summary of the actual device information, kind of like Netflow, but it's about the entire device, not just the networking traffic. So it's not flow information, but it's going to alert you about bandwidth usage, CPU utilization, disk space, or even traffic patterns that are easily identified, like floods or denial of service attacks. And by the way, you probably recognize these graphs here because they are widely used all over the world by a lot of hosting operators and networking engineers. Well, that's it for today. Make sure you understand the importance of capturing traffic, a couple of methods of doing so, and the difference between capturing the entire traffic and just looking at the flow information. Make sure you can define all this for the exam and for your daily operations. And one more thing, I would strongly advise you to give it a try and play with Wireshark on your own. It's free to install, anybody can use it. Try to capture some traffic, try to determine what type of protocols are in there, try to recognize the things that you know about IP packets or TCP traffic, and try to recognize them in real life traffic. That's going to help you tremendously recognizing these outputs and also troubleshooting real life issues that might appear in your environment. If you found this useful and easy to understand, make sure you like and subscribe. And see you next time, because we're going to talk about active defense. Now that sounds cool. Bye bye.